Hello friends, today we'll look at constraint satisfaction problem. As the name suggests, whenever we are solving a problem, we need to follow the constraints which are associated with that particular problem. So let's look at it. So constraint satisfaction problem, that is CSP, represents a class of problems where there are some restrictions between objects within that problem. So formally we can say CSP is a three tuple X, D and C, where X represents set of variables X1 to Xn and D represents set of domain variables D1 to Dn. C is set of constraints where each constraint is relation over a subset of variables. Fine, it's a formal definition of CSP. In short, what we can say is CSP is set of variables x1 to xn to which the values d1 to dn from a domain D can be assigned. So what we are doing here, we have set of variables, right? And we have set of domain variables. Now, the job is here is what? Assign the domain value, domain variable to variable. But when you're making the assignment, you need to follow certain constraints, right? You need to satisfy certain constraints, right? So what is the solution? A complete variable assignment that is consistent. That means complete assignment of domain values to the variables. And when you're doing the complete assignment, it should satisfy all the given constraints, right? So when the assignments are made, there is something called states explicitly represented as variable assignments. Then we have goal test. What is goal test? The set of constraints specifying allowable combination of values for subset of variables, right? Remember again, I read it. The set of constraints satisfying allowable combination of values for the subset of variables. So important is what? Allowable combination of values. This concept will be clear as we go ahead and look at some examples. Now, to solve any CSP, the best thing is to convert it into a graph problem, right? And here it is not a simple graph, it is a constraint graph. So we are converting a CSP problem into constraint graph to solve it in a optimal way, right? So binary constraint satisfaction problem, each constraint relates at most two variables, right? Which are those two variables? You have x1 and you have d1, variable and domain variable. Binary constraint graph, nodes are the variables and R's are the constraints, right? Usually in case of graph is what? It's a combination of nodes and the edges, vertices and the edges, right? So vertices are nothing but the nodes and the edges are the arcs, right? Now, if there is an edge between two nodes, then we say there is a relationship between these two nodes, or there is some constraint. So general purpose CSP solvers make use of graph structure to speed up the search. Let's take a very simple example here, constraint graph example. So here I have a problem is converted into constraint graph where I have four nodes, right? And the edges between the nodes representing the constraints, right? Now, if you represent it using CSP, then you have again three tuple, variable, domain, and constraints. Now, what is the variable here? Variables here are 1, 2, 3, and 4. What are the domains? Domains are red, green, and blue, right? So, what is a constraint? You can color these nodes in such a way that, and when you're coloring it, you'll be using only these three colors. And when you color this, you should color it in such a way that no adjacent nodes can have same color. No adjacent nodes have the same color, right? What does that mean? What is the constraint then? Node 1 and 2 cannot have same color. Why? Because 1 and 2 are adjacent to each other. 1 and 3 cannot have same color. 1 and 3 are also adjacent to each other. Similarly, 1 and 4 are also adjacent to each other. So 1 and 4 also cannot have same color, right? Similarly, 2 and 4. 2 and 4 are adjacent to each other, so they cannot have the same color. Similarly, 3 and 4 are also adjacent to each other, so they cannot have same color, right? So this is just a very simple problem which is converted into a constraint graph where nodes represent the variables, and the edges represents the constraints. What needs to be satisfied whenever assigning a domain value to the variable. Fine. Let us see how we can solve this. So to solve any CSP problem, backtracking algorithm is the best approach. Fine. It gives you the good solution. Fine. So let us start. So these are my variables 1, 2, 3, and 4, right? And initial domain is what? RGB, RGB. Now, what does this mean? For variable 1, initially I can color either red or green or blue. Similarly, for variable 2 again, initially I can give a color as red, green or blue. Similar is the case for 3. Either it can be red, green or blue, and similar is the case with the node 4. Fine. So this is the initial step. Now, let us select one of the node and start coloring it. So we start with the node 1. Fine. And I color that node as red. Right. So node 1 out of RGB is colored as red. Fine. Now, when node 1 is colored as red, all its adjacent nodes cannot be colored red. Right. What is a constraint? No two adjacent nodes should have same color. Now what I have done? I've colored this node as red color. So which are the nodes adjacent to it? Nodes adjacent to it are 3, 4 and 2. The edge indicates adjacency. They are adjacent to each other, right? So now 2, 3 and 4 cannot have red color. Fine. So what color 2 can have? It can have either green or blue. Similarly, 3 also can have either green or blue, and 4 also can have either green or blue. Is it clear? Now, let us color the second node. Fine. So we decide to color the second node as green. This is red. Now this we are coloring as green. So one is red, second is green. Now for third, now third is not adjacent to 2, right? Third is not, because there is no edge in between 2 and 3. So they are not adjacent to each other. So still third can be colored either as green or as blue. Fine. But when you look at the edge vertices or the node 4, it is adjacent to 2 as well as it is adjacent to 1 as well as 3. But right now we have colored 1 and 2, right? 1 is red color, 2 is green color. So for 4, the only option remains is blue color, right? Because 4 is adjacent to 1 as well as 2. It cannot have the color what is given to 1 and what is given to 2. 1 is red, 2 is green. So the only color what remains for node 4 is blue. Right? Okay. Now let's color the third node. Now third node, we color it as blue. Right? Because we had the option. It can be either green or blue. This is red, this is green. And the only option remaining for 4 is blue. Now we have colored 3 as blue. Now what is happening? 3 and 4 both are adjacent to each other. We can see an edge in between, right? And these two adjacent nodes cannot have blue color, right? This is violation of the constraint. So what is the solution? What we do? We undo this, right? We undo this assignment of blue, go back to the previous step, right? And select the other option. So what is the other option remaining now? Other option remaining is green, right? Blue is violating. So go back. This is backtracking and select the other combination. Now the other combination remaining is green. Fine. So now what is now there is no violation. Red, green, blue, green. Fine. Now 3 and 2 both can have green color because there is no connectivity. They are not adjacent to each other. Fine. So the final solution, you get it like this. 1 is red, 4 is blue, 2 is green and 3 is green. 1 is adjacent to 2, 3 and 4, right? So all these 3 have different color as compared to 1. 3 and 2 can have same color because they are not adjacent to each other. I hope it is clear. Okay. Another thing what we can do is we can use heuristic here. Even for this constraint satisfaction problem, we can use heuristic. What heuristic does? Heuristic gives you some extra information to solve the problem with less time, right? You can get the solution faster. So here, let us say you have a star graph, right? With the nodes 1 to 7, right? The constraint here is what? All the nodes can be colored only using two, red and green. Fine. So what is the set of variables? Set of variables is 1, 2, 3, 4, 5, 6 and 7. What is domain? Domain is red, comma, green. Fine. What is the constraint? Constraint is same. No two adjacent nodes can have same color. No two adjacent nodes can have same color. Fine. Now, if I want to do all the trial and error by assigning, again backtracking, again changing the color, how many possibilities are there? Because we have two colors and 7 nodes. So 2 raised to 7, that is 64. Fine. So we have 64 different assignments possible. So instead of trying these 64 different assignments, what we can do, we can use the heuristic. What heuristic we are using here? We'll select the node with the highest degree to color first. Now, if you look at all the nodes, which node has highest degree? 6 degree is only 1 because there's only one edge. 2 is also 1, but if you look at 1, it has 1, 2, 3, 4, 5 and 6 edges connected to it. So degree of 1 is 6, degree of 6 is 1, degree of 2 is 1, degree of 3 is also 1. So which node we select first to color? The node with highest degree. So node with highest degree is 1. So what we do? We color 1 as red, right? Now, once you color the node 1 as red, now 1 is adjacent to all the nodes. You can just see all the remaining nodes. 1 has or is adjacent to all the remaining nodes. When you already color this as red, then the only color remaining to color all these nodes is green, right? So remaining possibilities are only 6. This is 1 and remaining possibilities are only 6. Is it clear? So this is the solution. You color the node with the highest degree and the adjacent nodes are all green. Now, why they all are green? There is no violation because 6 and 2 are not adjacent to each other. There is no connectivity. 2 and 3 are also not adjacent to each other. There is no connectivity. Fine. Similarly, 3 and 4, 5 and 7, 7 and 6. Is it fine? So using heuristic, we could get the solution very fast because the remaining possibilities were only 6 and only one color was remaining. Fine. A very famous example of constraint satisfaction problem is map coloring. So let's look at this example now. So map coloring CSP requires that you assign a color to each region of a map such that any two regions sharing a border have different colors. The constraints for the map coloring problem can be expressed as follows. So what are the constraints? Each region is assigned one color only, right? Because it says there are many regions in the map. So each region is assigned only one color out of n possible colors, right? You are given a set of domain. This n is nothing but the domain variable 1 to n, right? From these, you have to assign a color to x1 to xn regions. But each region can be assigned only one color. Fine. The color assigned to one region cannot be assigned to adjacent region. The same thing what we saw just now in the graph. Two nodes which are adjacent to each other cannot have the same color. Similarly, here it is what? Two regions which are adjacent to each other cannot have same color. Fine. So we have taken an example of India, map of India, right? And the northern side of India. So we have northmost, we have Ladakh, Jammu Kashmir, Himachal Pradesh, Punjab, Haryana, Uttarakhand, and New Delhi. This is the part of the map what we are considering for our map coloring example. Now, what is expected here? We first need to find out which states are adjacent to each other, right? If you look at Ladakh, Jammu and Kashmir and Himachal Pradesh are adjacent to each other, right? So when you're coloring Ladakh, the color of Ladakh should be different from Jammu Kashmir and Himachal Pradesh. If you look at Himachal Pradesh is adjacent to Ladakh, Jammu Kashmir, Punjab, Haryana, Uttarakhand. Fine. So here when you are coloring all these neighboring states, the color of Himachal Pradesh should not be same as Jammu Kashmir or Punjab or Haryana or Uttarakhand or Ladakh. It should be different, right? So what we do now, we try to convert this graph into a constraint graph problem, right? Before that, let us see how we convert it into map coloring formal definition. Right? So color each region of northern India using three colors, that is the domain red, blue and green, so that no neighboring territory has the same color. So formally we define CSP as XDC. What is X? All the state names. What we already saw, Ladakh, Jammu Kashmir, Haryana, New Delhi. Fine. What is the domain? Green, red, blue. So what it is? It's an assignment problem. What we are doing? We are assigning these colors to these variables. And when we are assigning these colors to these variables, we need to satisfy this constraint. What the constraint says? Adjacent regions can't have the same color. They cannot have the same color. Fine. You need to color all these states using only these three colors. When you are coloring it, no two adjacent states can have same color. Fine. So variables are, I've given the short forms here: Ladakh, Jammu Kashmir, HPs, Haryana, Himachal Pradesh, Punjab, Haryana, Uttarakhand and New Delhi. Domains again red, green and blue. Constraint: adjacent regions must have different colors, right? So implicitly what we say, Ladakh is adjacent to Jammu and Kashmir. So Ladakh and Jammu Kashmir cannot have same color. But what Ladakh and Jammu Kashmir can have then? If Ladakh is red, Jammu Kashmir can be green. If Ladakh is red, Jammu Kashmir can be blue. They cannot be same. So what is the solution? Solutions are assignments satisfying all the constraints. Fine. Now, look at this graph now. This is a map which we converted into a constraint graph. Look at Ladakh, right? This node represents Ladakh. What is adjacent to Ladakh is Jammu, Kashmir and Himachal Pradesh. So this indicates the adjacency, right? These are adjacent to each other. So to Ladakh, adjacent is Jammu, Kashmir, there is an edge. To Ladakh, adjacent is Himachal Pradesh, there is an edge. Fine. We have converted this map into graph problem, constraint graph. Fine. So this is clear. Ladakh adjacent Jammu Kashmir, so one edge. Ladakh adjacent Himachal Pradesh, so one edge. Fine. Now look at Jammu Kashmir. Jammu Kashmir is adjacent to Ladakh, Himachal Pradesh and Punjab. So Jammu Kashmir is adjacent to Ladakh, Himachal Pradesh and Punjab. Whenever there is a relation, it is shown with an edge. Fine. If you look at Himachal Pradesh, it is adjacent to Ladakh, Jammu Kashmir, Punjab, Haryana and Uttarakhand, right? So all the edges from Himachal Pradesh will go to all the states except New Delhi. New Delhi is not adjacent to Himachal Pradesh. It is adjacent only to Haryana. So there is only one edge, Haryana to New Delhi. But Himachal Pradesh is adjacent to Ladakh, Jammu Kashmir, Punjab, Himachal Pradesh, Haryana and Uttarakhand. Fine. And if you look at Punjab, Punjab is adjacent to Jammu Kashmir, Himachal Pradesh and Haryana, right? Jammu Kashmir, Himachal Pradesh and Haryana. So I hope this is clear. Converting a map into constraint graph. And constraint is represented in the form of an edge. If an edge exists, you need to follow the constraint. Fine. Now, what strategy we are using? We are using a backtracking strategy. This strategy involves checking the constraint after each assignment on a single variable, right? So if some constraints are violated, this strategy backtracks to the previous choice, undoing the assignment and tries another assignment. So suppose our strategy, we start with the empty assignment, right? Let us say we pick up Ladakh first. We can pick up any one, but we start with Ladakh. Now, what is the possibility for Ladakh? We can have three domain variables available for Ladakh in the beginning. It can be colored as red, it can be colored blue, or it can be colored green. Now, what we do in the case of strategy, we select one of the assignment and we check the constraint. is there is any constraint violation. If there is a violation of the constraint, what we do? Backtrack and assign another color to Ladakh, right? A very simple example. Let's look it in a very simple way how backtracking will work here. Pick a variable to assign. The variable here is a state, northern states of India. Pick an assignment for the variable. Now the assignment for the variables are nothing but the colors red, blue and green. Check if all the constraints are satisfied. What are the constraints? No two adjacent states can have the same color. If the constraints are not satisfied, then try a different assignment. That means whatever color you assign, undo it and assign a new color. If no assignments left, you need to backtrack. If the assignment is complete, then we have the solution. Fine. I hope this simple flow of backtracking search is clear. Now, let's apply it to our example of northern states of India. The first time I color Ladakh as red, right? After coloring Ladakh as red, I come down, right? I color Jammu Kashmir as green. But then I have some problem. If the constraint is violated, I go back again, change the color of Jammu Kashmir to blue. But still there is some issue with the constraint. So I go back again. See, this is backtracking. I go back again and undo the red color of Ladakh, right? And then color Ladakh again as green and again follow the same procedure till I get all the constraints satisfied. This is just a flow to show your backtracking search. Fine. So what is the solution then? Solution is Ladakh should be colored green, Jammu Kashmir red, fine, Haryana red, Punjab green, Uttarakhand green, New Delhi blue, and Himachal Pradesh also as blue. So see, we have colored our nodes, right? Ladakh is green, Jammu Kashmir as red, Himachal Pradesh as blue, Punjab as green, Haryana red, Uttarakhand green, and New Delhi as blue. Now, what you need to check? You need to check whether there is any constraint violation. So, what constraints are? No adjacent nodes can have same color. When do we say nodes are adjacent? Whenever there is an edge in between, right? Now, let's look at Himachal Pradesh first. Himachal Pradesh is connected to Ladakh. So, this is green, this is blue. No violation of the constraint. Now, Himachal Pradesh is adjacent to Jammu Kashmir. Jammu Kashmir is red. Himachal Pradesh is blue. No violation. Now, this again blue and green, no violation. Blue and red, no violation. Blue and green, no violation, right? So, there is no problem here. Let's look at Jammu Kashmir, right? Jammu Kashmir is adjacent to Ladakh, which is green in color. The colors are different, no issue. It is adjacent to Punjab also. Punjab is also green, no issue. Why? Because there is no connectivity between Punjab and Ladakh. Remember, the colors, nodes colors are same, but there is no connectivity. There is no adjacency relationship there. Similar in case of Jammu Kashmir and Haryana. Both are colored red, but there is no edge in between these two. So they are not adjacent to each other. So this is the final solution of coloring northern states of India. This is what it will look like. Now this makes it the picture more clear. No adjacent states have same color. Remember, these two are green, but they are not adjacent to each other. This is also green, but these are not adjacent to each other. And New Delhi, the smaller one, is only adjacent to Haryana. So I hope the concept of map coloring is clear. Another very famous example, what comes whenever we talk about CSP is Sudoku, right? Most of you all might have played it. So what it has a small grid of 3 by 3 grid, right? There are total 9 3 by 3 grids placed in such a way that they form a big square, right? Now, what is a variable here? Variable is set of these open squares. Each open square, right, is a variable. What is a domain? Domain is the number 1 to 9 which can be assigned to these squares. Remember, again, it is an assignment problem. Fine. So these squares can be filled with the numbers. And what numbers? From numbers ranging from 1 to 9. So when you are assigning these numbers to these squares, what is the constraint? The constraint is what? the column should not have duplicates. Now this column, right? It should not have any duplicate number, right? This should not have any duplicate number. This column should not have any duplicate numbers. What is the second constraint? The whole grid of 3 by 3 should not have duplicate values, right? It should have numbers only from 1 to 9. No number should be repeated, right? No duplicacy is allowed. Third constraint is what? Each row should have unique numbers, no duplicate numbers. Each row should have numbers only between 1 to 9 and these numbers should not be repeated. Fine. So, a simple CSP problem with the set of variables, domains and constraints. Again, this can be converted into a search space graph. And if you look at it, we have this solved example of Sudoku. If you look at the whole row, this row does not have any repetitive number. All numbers are between 1 to 9 and no number is repeated. Look at the column, right? This column does not have any duplicate number. Fine. Similarly, if you look at this 3 by 3 grid, this whole grid has number only between 1 to 9. You can just see 1, 2, 3, 4, 5, 6, 7, 8 and 9. No number is repeated. Right? So this is a solution for this Sudoku. I hope constraint satisfaction problem is clear. Thank you.